Hi everybody, we are going to get started with derivatives of log functions, which was covered in Calc 1. I'm just going to revisit a few things that might be helpful to remember. Everyone's favorite, of course, is logarithms. I'm going to focus on the natural log, but we'll do logs of a different base on another day. So everything I say here about properties and general idea of a sketch is pretty much the same. So if I just kind of look at this graph and just trace over it so I can see this, this is your natural log function. I'm just going to kind of trace right over that beautiful sketch that I screen captured there. I'm going to label this F. This is the natural log of x. And some nice things to know here. Notably, there's an x-intercept at x equals 1. So 1, 0 lies on this graph. That's one of your properties of the logarithms over here. Natural log of 1 is 0. That's the value of it. And we're good. It's nice to know that the natural log of e is 1. That's just nice in evaluating sometimes that you can knock out that logarithm if you see it. And then we have some properties. So let's get into the idea of these properties, which you might remember from an old previous math class, whatever that is, algebra, pre-calculus, Calc 1. They have certainly been in all of those classes as far as these properties are concerned. So if you have a product inside any logarithm, not just natural log, they separate into individual logarithms with a plus sign in the middle. If you have a natural log of a division, then those separate into two separate logarithms with a subtraction sign in the middle. And then here, when you have an exponential inside a logarithm, you are permitted to bring that power in front and then just have the natural log of the base. This is not a derivative rule, mind you. This is a property, but it feels like the derivative, certainly from Calc 1. So let's take a look at what our derivative rule is. And before we do that, actually, let me just do a quick example here of some of these properties, just to kind of mention it. If you have the natural log of 3 squared, that's the same thing as 2 times the natural log of 3, just kind of highlighting that idea, okay? If you happen to have, for example, let's say you wanted to look at the same exact idea, but in a different way. 3 squared is 3 times 3, and you could use that property of, hey, I can break these into individual logarithms, right? Like that's what this property says. That is great, and you can kind of see like, hey, those are like terms. That is the same thing as 2 times the natural log of 3. It's just nice to think about some of these properties, and you can take out your calculator and you can double check the numbers on these. It's really great that we can use these properties, and we are going to capitalize on that when it comes to our derivative process. So I'm going to slide down here just to look for a second. Here's the derivatives of our logarithmic functions. The derivative of the natural log is 1 over x. That's base e, right? And the derivative of the natural log of some other function of x here, you can kind of see that once you learn the chain rule, it's everywhere. The derivative is 1 over what was inside, and then you're going to chain it. So this is really just executing that chain rule for differentiation. And pretty much as soon as you learn the chain rule, they are always going to define new derivatives using that. So let's take a minute and just graph what 1 over x looks like. Now notice here, there's this statement that x can only be greater than 0, but it's non-negative. And really, or it's not 0 either. And that goes back to the domain of your natural log graph, right? So if I just slide up just a little bit, right? Your domain is 0 to infinity. So if your function is only defined from 0 to infinity, then your derivative can only necessarily be defined from 0 to infinity. So you can't have a derivative where the function doesn't even exist, right? And so I'm going to take a minute and just graph that derivative function. I'm not a magician or anything. I'm just going to kind of plot some points. That here's my derivative down here. If x equals 1, well, then the output of your derivative is 1. If x equals 2, then the output of your derivative is 1/2, and if x equals 1/2, the output of your derivative is 2. So I'm just kind of point plotting here a little bit, and I am going to draw the graph of the derivative of 1 over x. I'm going to label that as f prime. It's just nice to see a function and its derivative on the same set of axes so we can talk about it here. The domain of this function, of the natural log, remember, is 0 to infinity. That's why we have that kind of notation there on the derivative. It's only defined where x is greater than 0. The range of your natural log function is all real numbers, okay? And this function of the natural log is increasing, continuous, and concave down. Here's my derivative, okay, which shows the slope of this natural log function everywhere. Thinking about our old Calc 1 ideas, notice here that the natural log function is increasing everywhere. It makes complete sense then that your derivative values should all be positive, because a positive derivative tells you that your original function is increasing. So that makes sense that that is in fact happening there. All of your values of the derivative are positive. That means the original function is increasing on its entire domain. Okay, so while the natural log function, let me see if I can put in here, has a vertical asymptote at x equals 0, so does your derivative function. Okay, and it also turns out that the derivative has a horizontal asymptote at y equals 0. Just things to notice. Okay, let me switch back to my pen, and let's do a couple of quick derivatives here. It would be helpful to use some of those properties, going back to that, right? These will make our life easier. I promise, I promise, I promise. So I'm going to use some of those. So I am going to just rewrite problem number 1 here, right? I'm going to use some of those properties. I see inside here, I'm going to go ahead and put parentheses there. That means the natural log of 4 times x cubed. I'm going to rewrite. I'm not taking the derivative, mind you. I'm just going to say, look, using those properties, you're allowed to rewrite your expression or your function like that. That's legal. That's a property. That's not a derivative. I can also keep going with this rewriting idea and say, I can even bring that 3 in front as a coefficient, so that's awesome. And the whole point of this is to make your original function just prettier. It's smaller pieces, easier to do, and so I'll switch to a different color to say, hey, now I'm actually taking the derivative. Let's go ahead and do that. The derivative of a number, this natural log of 4 is a value. I don't know what it is numerically, but it's a number. So the derivative of the natural log of 4 is 0. Okay. Over here, the 3 is just a coefficient that just kind of comes along for the ride. And using my rules up here, the derivative of the natural log of x is 1 over x. And it's pretty much understood that you wouldn't be evaluating the derivative where the function wasn't defined. So you don't have to worry about stating the domain on all of your derivative work. Not your job. Okay, so here is my derivative. Okay. Now, I'm going to use that strategy again on problem number 2. And by that strategy, I mean, let's use some properties and rewrite this in a more pleasant way, and then take the derivative. It's just a nicer way. I want you to be efficient. So again, I'm going to put those parentheses. The x to the 4th is inside that logarithm. And I'm going to take some time. Before I get going here, I'm going to use those properties and say, look, it is legal to bring that 4 in front of the natural log of x. That's just rewriting. That's not the derivative. Right here, I will take the derivative. I will switch back to red to say I am taking the derivative now. There's my f prime. The 4 is just a coefficient, comes along for the ride, and the derivative of the natural log of x, again, is 1 over x. So there is my derivative. Okay. Now, you didn't have to do it that way. Let's say you said, I did this in Calc 1 and I did a different way. Of course you can. Let's take a look at that. You could just do this directly, right, from here, using the chain rule. And let's investigate that. Say, I'm going to just take the derivative right off the bat. I don't want to use the properties. That's okay. You could say, okay, let me use that chain rule. I'm going to say the derivative of the natural log of something is 1 over that something, and then chain it. So x to the 4th was the something. Take the derivative of that, right? That's executing that chain rule that we have in that box up here. That's exactly what this guy is saying right there. If you notice, when you clean this up algebraically, guess what? All roads lead to that simplified answer. So it's totally appropriate. If you would like to use a chain rule, you certainly can. I'm just trying to give you some strategies of other things that you could use that might make your life easier. But honestly, go ahead. If you want to do this as a chain rule, that is great. You could have done the same thing on question number 1. You'll see it reduced down to 3 over x. So pause the video, check it out, see what you get. When it comes to question 3, the reason I have these side by side is because I want you to visually see the difference in these functions. This has the power of 4 attached to the x, which is inside the logarithm. This is a totally different function, and you have to make sure your eyeballs are really paying attention. This is taking the natural log function and raising that whole thing to the power of 4. That is different. You absolutely cannot use any log properties on this. They just don't apply. This is a straight up chain rule, and I'm going to have to get going. No properties apply to this. So I'm going to switch to red because I'm just going to get in there and start taking the derivative. And so this is that general chain rule where I'm going to say, let me take the derivative of the outside function. In this case, you have something raised to the 4th power, so that 4 comes in front and you reduce the power by 1. The hardest part of the chain rule is to not mess with that thing inside. Remember, you chain that after the fact. So the derivative of the natural log gets taken care of outside of that generic chain rule that we had going on. So here is my derivative. Honestly, I think that looks great. I think maybe we'll regroup and just make it look, a little bit more, I don't know, pretty. You have to make sure you're communicating your answers well. I mean, bad handwriting can get people in a lot of trouble, and I don't want that to happen to any of you. So there's just a couple of basic derivatives. Okay, we'll also do a few more. We'll also do things like this, where, okay, maybe I have a natural log with other kinds of functions. This would definitely be your product rule that you learned back in Calc 1. Slide so you can all see that. Again, there is no property here on how to break up this logarithm. You can't. Okay, that 3x minus 8 is inside the logarithm. There is no property that addresses that. I just have to get in here and take the derivative, and I think for the sake of having a different notation, I'm going to use dy dx. I could use y prime. I could use dy dx. Doesn't matter. So I'm going to use the product rule, which I might write differently than you, but order doesn't matter in the product rule, right? Because there's an addition between the two terms that you get. So let's think about the product rule, right? It's you have these two functions. It's the derivative, it's the first times the derivative of the second, plus the derivative of the first times the second unchanged. That's pretty much where we're headed. Okay. So we practiced all of that. So I'm going to do that here. I'm going to say x squared unmessed around with. Now the derivative of the natural log of anything is 1 over what was inside, and then I'm going to chain it. So that's why I have a 3. The derivative of 3x minus 8 is 3. Then I'm going to add to that the derivative of x squared times that natural log function unchanged. So that is my derivative. I might take a minute and rewrite it. Totally up to you on how far you want to go here. But you want to make sure you're communicating your answer well. So that's a good looking derivative. You might find that the textbook will get a common denominator in this case, so it's worth mentioning. If I were to do that, I would actually multiply this guy by a 3x minus 8 as well. So why not? We'll just do it. I'd have another factor of 3x minus 8 here. And you might see them kind of do something like that. It's algebraically the same answer. It doesn't matter. Just a different way of writing it. So be flexible, if you're going to check your answers with the textbook or anything like that. Okay, there'll be some extra problems if you need extra practice. All right, in here we have a straight up quotient rule. All of our greatest hits of Calc 1 are coming back here. So you need to make sure that you're comfortable with anything thrown at you from Calc 1. This is Calc 2, so we should be able to do that. I will get in here and I will use some notation. I'm going to go back to y prime, why not? Remember with the quotient rule here, you always kind of put this over the denominator squared. There it is. And in the numerator, the order does matter on the quotient rule because there is a subtraction in that numerator. So, so here's what I'm going to do. I'm going to do bottom unchanged. That's how it has to begin. Times the derivative of the numerator minus the numerator times the derivative of the denominator. Order matters. You cannot mix up the quotient in the numerator in that quotient rule. You can't say, oh, it was good, except I got it backwards. Then you miss the whole point of the quotient rule. Okay, so pay attention, be careful, all of that stuff. I am going to clean this up slightly just to make it look better. I always like to clean up negatives because they bother me. So I'm going to go ahead and distribute this 1 over x to both of those terms. And I'm going to clean up the double negative in there, right? That's positive 2x natural log of x. Oops. And there's that denominator. Now, math people do not like the way that this looks because there is a fraction in a fraction. That is a complex fraction. So I'm going to handle that really quickly. And it's not the first time you're going to do something like this. I'm going to multiply by 1. But I am going to make 1 look really weird. I think we all agree that x over x is 1. Just like 5 over 5 is 1 or 8 over 8 is 1, right? So I'm multiplying by 1. So I'm not going to change the value of this expression, but I am sure going to change the look of it. And the reason I chose x is because that's that little denominator there I want to get rid of. I'm going to multiply everybody by an x. Everybody gets an x. So that means my new numerator, I'm going to cancel the x's here. It's just a 1. That's the whole point. But everybody gets an extra x. So now instead of negative x squared. Now instead of that term there, I have positive 2x squared ln x. And don't forget about the denominator. You have that extra x happening in the denominator as well. And so here's a really good looking clean answer that makes math people happy because there is no complex fraction remaining. So just a quick cleanup method. All right. Now, when it comes to number 6, I do not need to do anything crazy here. I am not going to do a straight up chain rule. What I'm going to do here is I absolutely can go back and use some of those properties. This would be so great if I could tone this down a little bit, and you can. This is legal. This would be a great time to say, oh my goodness, I have a logarithm with a quotient in there. Let's use those properties. Notice I'm not using primes. I'm just going to say, look, it's natural log of the numerator minus the natural log of the denominator. This is legal. Okay. And again, just take a difference at these two equations, right, between 5 and 6. In 5, that 1 minus x squared was the entire denominator, right? Had nothing to do with the logarithm. That's why I had to use the quotient rule. But here, all that stuff is in the natural log. You can use those properties and clean it up. So now that I have it separated, I just used a property, so it's the same equation, just a different look. Now I will get in here and take the derivative. So I can use dy dx or y prime, whatever you feel like. And I'll go ahead and take this derivative. So the derivative of the natural log of x is 1 over x. And over here, I'm going to have to incorporate that chain rule. So the derivative of the natural log is whatever, 1 over whatever's inside. And then I'm going to chain it. So that means I need a negative 2x. Certainly, I'm going to clean that up a smidge. And I think that looks like a great derivative. I think that's wonderful. I think you might be required to get a common denominator for some reason, so let's just go ahead and do it. If I were to do that, getting a common denominator, then my common denominator would be x times 1 minus x squared. So in this fraction, I already have the x. I would just have to multiply the numerator by that factor of 1 minus x squared. And in this guy, I already have the 1 minus x squared. I'm missing that factor of x. So let's just rewrite it. Again, it's the same value. I'm just making it look different or prettier or whatever you want to say, right? So I'll work on that numerator. And then I'll clean it up. So what is that? 1 plus x squared, and then your denominator is x times 1 minus x squared. So that's another look, another version of the derivative. Okay. All right. So rounding out all of this stuff, what I was trying to get us ready for is to be able to handle something like this problem, which is problem number 7. Okay. This is a different question. You may have done this in Calc 1, you may not have. You can kind of notice, piggybacking on that derivative refresher that you probably looked at already, I see that there is no y equals in this equation. All the others had an f of x equals or a y equals. This has x's and y's all jumbled up. So what's going on here? This is your implicit differentiation. So when I talked about the greatest hits of Calc 1, this is definitely in your playlist, right? So I'm going to go through the process of implicit differentiation here. And again, I'm kind of running through this stuff. You can pause the video. That's the great thing about an online class with videos. You can pause it, catch up, replay it, stuff like that. So I am going to get in here with this implicit differentiation, and I've got a lot going on. I've got to handle the product rule here to begin. And I have another product rule over here. So you've got a lot of work cut out for yourself here. So I am going to switch to red since I tend to be using red for I'm taking the derivative now. So let's go ahead and do that. So on this first puzzle piece, I need a product rule. So that's going to be first unchanged times the derivative of the second. I took the derivative of x, so there's no extra puzzle piece. When it comes to the other side of that product rule, when you take the derivative of y squared, it is 2y. Go ahead and do it. But when you take the derivative of the y variable, you have to throw in that dy dx. Okay, that's how implicit differentiation works. You just kind of do it. And if you take the derivative of the y variable, you slap a dy dx on it. Now, I'm going to leave the natural log of x alone because I wasn't taking the derivative of that. So that's all one giant term there. Okay, now I'm going to do the same thing on this 3xy. So I have a positive in there. So let me go through the product rule here. I'm going to consider it like 3x times y. So 3x unchanged. I'm going to take the derivative of y, which is 1, with a dy dx, because that was a y variable I was working on. I'm going to add to that the derivative of 3x is 3, and then just times the second equation, or the second term, unchanged. There's no dy dx here because I wasn't taking the derivative. Paying attention here, the derivative of a number is 0, and there's my equal sign. So this is a lot, right? I have all these terms, I got everything going on. I'm going to try to regroup just a little bit, just to kind of play around with this a little bit. I've got y squared over x, just to see that as one term. I've got 2y, natural log of x, and then that's got a dy dx attached to it. I've got 3x, I don't really need the 1, that's got a dy dx attached to it, and then that 3y. And how we handle the implicit differentiation is anything with a dy dx, group those together, and anything without the dy dx, throw it on the other side of the equation. I don't care which side any of this stuff goes on, it doesn't matter. But because I already have these dy dx's here, let me leave these guys here, these will stay, and that means I'm going to throw the other terms over to the other side of the equation. So let's regroup. These two terms with the dy dx are going to stay exactly where they are. But these other two terms are going to slide over. That means the 3y is negative. That means that y squared over x is also negative. And the point of doing that is so now I can kind of look at this and say, oh, everything with a dy dx, guess what? That's now like a GCF. I'm factoring on the left-hand side. So let's go ahead and take that out, that common factor of a dy dx. That happens to be exactly what I'm trying to find, right? I'm trying to find the derivative. There it is. And then I don't really mess with this side. It just kind of is. And if I wanted to solve for dy dx, which is the point of this question, let's be honest, I'm going to get that pretty easily if I just divide both sides of the equation, right? I'm going to do the same thing to both sides. I'm going to divide by 2y, natural log of x, plus 3x. 2y, natural log of x, plus 3x. Boom. There is my derivative. It doesn't look great, but it's correct, right? So let me write that down. dy dx is negative 3y, negative y squared over x. There's my denominator. Now again, math people don't like this because there's a fraction and a fraction, and remember what we did last time. You can do whatever you want, but I am going to get crafty, and I'm going to say, oh, I really want to get rid of that x down there. Let me multiply by 1. And I'll make 1 look like x over x again, because that's going to solve my problem. I'm going to make sure everybody gets multiplied by x, of course. That's the only way this strategy works. And so what do I have? Well, I'd have negative 3xy from that x being thrown in. Here, the x cancels that denominator. That was the whole point of doing that. And in the denominator, you're going to creep an extra x into each one of those terms. That is a great looking derivative. Okay. Now, just for the sake of argument, if you happen to move the dy dx's in this step over here over to the right-hand side, right? Instead, if you move those over to the right instead of keeping them on the left, what ends up happening is you get the same value, but I'm going to put an equal sign here just to show. This is an equivalent answer. I could be off by a negative on every single term. And if you're off by a negative on every single term, that is an equivalent answer. So I just want to write it down for those of you that maybe worked ahead on the video and were like, wait a minute, I didn't get the right answer. This is absolutely appropriate. It's equivalent. So I just want to throw that out there. All right, so now the last derivative that we're going to do, again, another implicit derivative, well, in this video anyway. So let's get in here and do this one. So on this implicit differentiation problem, I can see that it's implicit because the x's and y's are all jumbled. There's no y equals or f of x equals. I'm just going to get right to it and work on the derivative here. I'm going to do so implicitly, and I am going to be careful. Now, there is no property, once again, to address the natural log of a minus b. That was not on our list. I want to be clear about that. There is no property to make our life easier here. We are just going to get in here. We are going to do the derivative, and we're going to work on chaining it. So the derivative of the natural log is 1 over whatever is inside. So let's do it. Now, here is where I chain it. So I need to multiply by the derivative of 3x minus 2y. The derivative of 3x is 3, and the derivative of negative 2y is negative 2, but you need that dy dx on there to say, hey, I just took the derivative of the y variable. Let me state that. Okay, so left-hand side of this equation, we are done with the derivative. Right-hand side, again, I've got a product rule, so I'm going to work that out. I'm going to say, let's think about it as 4x squared times y. I'll leave the 4x squared unchanged. The derivative of y is 1, dy dx, of course. And then I'll add to that the derivative of 4x squared, which is 8x, and then leave the y alone. We're not taking the derivative of it, so I'm just going to leave the y. No dy dx needed. So here I have a pretty complicated expression, but I am just going to handle it with my Algebra 1 skills. I'm honest about that. Please, let me know if anything seems weird. You have a expression here, I guess this term, multiplying a binomial. So I'm just going to work that in. I'm going to multiply it by 3 and multiply it by negative 2 dy dx. I'm going to separate these. Let's actually do that. So if I do that, 3 times this fraction, what does that give me? Well, let me switch back to red. That would give me 3 over 3 minus 2y. If I multiply this fraction times that guy over there, what would I have? Well, I would have negative 2, 3x minus 2y, and then that extra dy dx. I'm just going to kind of keep that off to the side. Over here, I don't know. I guess I don't really need the 1 going on there. I'll just say 4x squared dy dx plus 8xy. Now, it does not matter which side of the equation you move all your dy dx's to, but we are ready to start moving because I have all of these guys individualized. And I think for the sake of argument, let's move all the dy dx's to the right-hand side this time. So that means I'm going to leave the 4x squared dy dx on the right. I'm also going to move this term. So it's going to hop over and become positive. But I'm going to take that 8xy, I'm going to move that over to the left because that does not have a dy dx. So the term that's going to stay here is the one that didn't have a dy dx. And then this guy kind of comes on over because it also does not have a dy dx. So you can kind of see you have your haves over here. They have a dy dx. And your have-nots. They do not have a dy dx. Now, I am ready to recognize over here on the right-hand side that since they all have a dy dx, I'm factoring out the dy dx. That's exactly what's going on. I'm going to say, look, I see that both of those terms have a dy dx. Let's factor it out and see what's happening. Okay. I didn't do anything over here on the left. I'll just kind of rewrite it, I suppose. And your point to this problem is to find dy dx. So let's divide dy dx by whatever's multiplying it. So here we go. Okay. That right there on the left-hand side is my derivative. Doesn't look so great, but that's okay. We will figure it out and we will work on it. So what does that mean? Okay, so math people do not like this presentation of the derivative. It's too junky. We're going to clean it up. And we're going to do it pretty quickly. So I'm going to just label the dy dx over here. That is dy dx. Okay, math people don't like it. What am I going to do? I'm going to multiply by 1. I'm going to get creative with what I'm going to let 1 represent, right? It could be 10 over 10. It could be 2 over 2. I'm going to decide in this problem, since I really want to get rid of those denominators of that 3x minus 2y, that's the whole problem that math people have. Well, let's make 1 look ridiculous. Let's make it look like 3x minus 2y over 3x minus 2y. That really is 1. I'm going to multiply everybody by 3x minus 2y, everyone. The point is to get rid of the denominators here, right? So that's going to cancel out that denominator, leave me with 3, which is great. Over here, I'm going to have the negative xy, but that 3x minus 2y is multiplying that. But that's okay, I've gotten rid of the fraction in the fraction, so great. I'm going to keep going in the denominator. So 4x squared is also going to have an extra factor of 3x minus 2y, plus sign in the middle, and then you kind of knock out your denominator there. So this is great. This is a much better form for the derivative. I think this looks great. I think you might want to keep going and write it a little bit nicer. We are definitely not going to cancel these common factors. There are 2 separate terms going on in here. So I'm going to urge you to keep going and let's clean this up. That numerator, the 3 is just hanging out. But I have negative 24 x squared y. And then my next term would be positive 16 xy squared. In the denominator, I'm going to multiply that 4x squared through. That will be 12x cubed minus 8x squared y plus 2. So there is my derivative. I am going to box that up. That's a much better answer than putting yourself in some kind of weird algebraic moment here. Multiply everything out and you are protected. And it's okay, right? In these last 2 examples, your equation that you were given was an implicitly defined equation. X's and Y's were jumbled up. So it's okay that your derivative has X's and Y's all jumbled up. Totally appropriate. Same thing on example 7. Okay, so it's okay that you have a derivative in terms of X and Y. All right, in our next video, we'll get into some more problems.